So this is related. This session is related to the resultant force as we discussed in the yesterday's class. And we discussed Newton's law. According to Newton's first law, that an object will be at rest if the resultant force is zero, or object will continue to move. So if the resultant force is zero, what are the two possibilities? The object will either be at rest or it will continue to move with a constant velocity. And what about the Newton's second law? It states that whenever there is a resultant force act on the object will accelerate, and acceleration is proportional to the resultant force. So resultant force and acceleration are directly proportional, or we can relate that F is equals to ma. This is when object is accelerating or decelerating. So yesterday we did some examples related to the inclined surface. Object is on the horizontal surface, or two objects are connected by a string or a wire, and objects are connected by a pulley and a string. Today we'll discuss about how we use this concept in elevator or lift. So how we can use this concept. Example, this is a lift or elevator and it is attached with a cord, and you have an object on the floor. It can have like different conditions, different cases are there. So we are discussing the first case in which either it is at rest or it is moving with a constant speed or constant velocity up or down, because the direction here in this example does not make difference if it is moving at a constant speed. So object is lying on the floor, weight of the object, if you draw the free body force diagram, the weight of the object is acting downward, and the normal contact force, the force from the surface, is acting upward. And same way you have another object which is attached with a spring. So if it can be attached with a string or it is attached with a spring. So when we draw the force diagram, free body force diagram for this object, so its weight is acting downward, and the tension, the force by the spring, the restoring force of the spring, that I'm representing by T. So T is acting upward. Now, because this object, like this lift, is either at rest or it is moving at a constant speed, so in that case the resultant force will be zero. So if resultant force on the lift is zero, it means the resultant force on the objects which are inside the lift will also be zero. So all these objects will have no resultant force. If we consider the whole lift, it will not have any resultant force. If we consider the object which is on the floor, that will not have any resultant force, and we consider the object which is attached by a spring or a string, will also it will not experience any force. So when we write the equations for object which is on the floor, so upward force minus downward force, or downward force minus upward force, the resultant will be 0. Or we can say that weight will be equal to normal contact force. Like example, if weight is 30 Newton, the normal contact force will also be 30 Newton. And what about the object which is hanging? The weight is acting downward and the restoring force or the tension is acting upward to pull it, and the result should be zero because it is not accelerating, it is either at rest or move with a constant speed. So if we write the equation, we can say W is equals to T, or we can say weight will be equal to tension. So if weight of this object is 10 Newton, how much tension will be there? That is also 10 Newton. Is it clear? The first case in which the object is either at rest or move with a constant speed. That's the first condition for object inside the elevator, and the elevator is either at rest or elevator is moving at a constant speed. So the resultant force should be zero. Then the second scenario, that the elevator, if it is accelerating upward or decelerating downward. So accelerating upward or decelerating downward have the same meaning. How they have the same meaning? Because if it is accelerating upward, it means the upward force is greater, or if it is decelerating downward, that also means the upward force is greater. So if we say it is accelerating up or we say it is decelerating down, that having a same meaning. It means the upward force is greater than the downward force. And we are again taking the two objects. One is on the floor, another one is hanged by a wire. You can have a wire, you can have a string, you can have a spring here. So because it is accelerating upward, so the acceleration of the lift, the value of acceleration of the lift will be same as acceleration of the object which is on the floor, and that is same as acceleration of object which is hanging by a string. They all have the same acceleration, that's why they remain in the lift. So when we draw the free body force diagram for object which is on the floor, the weight of the object is acting downward, and the normal contact force, the force from the surface, is acting upward. So if we write an equation for object on the floor, so we know that it is accelerating upward, so means upward force should be higher and downwards, and there should be a resultant force on this which is equals to ma. So when we write the equation for object which is on the floor, so there should be a resultant force, and that is equals to ma. And what about the resultant force on this object which is on the floor? R is acting upward, so it will be R minus W. Why I am writing R minus W? Because R is greater force as it is accelerating upward. So R minus W is equals to MA. Or we can say R is equals to W plus MA. Or normal contact force will be equal to weight plus ma. So it means that in this scenario, what it appear? It appear that the apparent weight, not the actual weight, but it appear that the apparent weight of object will increase. So whenever an object is accelerating upward or decelerating downward, what happened? Our actual weight, what is our actual weight? But if it the object, like example, if I say the actual weight or original weight is 100 Newton, but what happen if the lift is accelerating upward? Then what it appear that our weight will increase, or it will appear more than 100 Newton. because the normal contact force, which is balances with the downward force, equal to weight plus ma. Is it clear, this idea? That if r, the normal contact force, increase, it means the downward force increase, and downward force appear to be our weight, so it appears that our weight will also increase. So our weight will appear more than 100 Newton whenever a lift is accelerating upward. And you can experience these things. You can experience this, like example, if a swing is there or a merry-go-round, you will feel when it is moving upward, you will feel heavier because your apparent weight increased or the downward force increased. Same way, if the object which is hanging or suspended by a string or a wire. So if we draw the free body force diagram for this object, the weight is acting downward and the upward force is there T. So it will be T minus W is equals to Ma. Why T minus W? Because it is accelerating upward. So upward force should be higher, or we can say T is equals to W plus Ma. So the tension in the spring will increase. If tension in the spring will increase, what it appear? It appear that the object is heavier. Is it clear, this idea? When the lift is accelerating upward or decelerating downward, so what it appear? It appear that our apparent weight, the weight which appear, yeah, the gravity decreases with the increase in height, that's true. But what is our assumption? Because we are assuming that the value of the gravity is constant. It's not changing with height. Practically, yes, it changes with height, but that's not a greater difference in the height when the lift moves from one floor to another. That's why we are considering that the gravity is constant, and in this case, the apparent weight for an object, if it is accelerating upward or decelerating downward, will increase. Then, if lift is accelerating down or decelerating up. So lift is accelerating down or decelerating upward. So we have a lift here connected by a wire or a string. And this time it is accelerating down. So it means the downward force is higher. Or it can be same scenario. We can say it is decelerating up. That also means the downward force is higher. And we have two objects. One is on the floor. So weight acting downward and the normal contact force will act upward. So as the weight is acting downward, normal contact force is acting upward. Because it is accelerating downward, it means the downward force is higher and the upward force is smaller, and there should be a resultant force which is equals to ma. So for an object which is on the floor, W minus R is equals to ma, or it will be W minus ma is equals to R. So you can see the value of the R, the value of the normal contact force will decrease because that is W minus ma. So if the original weight of this object is say 100 Newton, what it appear, because it is W minus ma, so 100 minus some value, so the normal contact force will decrease. It means the downward force is decreasing, or it appear that the object is lighter or weight of the object appear to decrease. Because of the condition, the weight appear in practical, the weight is not decreasing, but because of the motion of the system, it appeared that the weight decreased, and that's why we call that as a apparent weight. So original weight is not changing, but because the downward force is changing, that caused the change in weight as well, which is a downward force. So it will be less than 100 Newton if the original weight is 100 Newton. And if we have an object which is attached by a wire or a string, so weight is acting downward, tension is acting upward. So for an object which is hanging, it will be W minus T is equals to MA, or we can say W minus MA is equals to T. So in that case, the tension, the force of the spring will decrease. If force of the spring is decreasing, it means what it appear that because it is representing the weight as well or downward force, so weight will decrease or apparent weight will decrease. Is it clear, this idea? The three conditions for object inside the elevator or lift. First one, if object is at rest or if the lift is at rest or move with a constant speed, the apparent weight will be same as the actual weight. But if it is accelerating downward, the apparent weight be higher. If it is accelerating downward, apparent weight will be lighter, and if it is accelerating upward, the apparent weight will be higher. So another topic which is also related to this, you should be able to use the equation that the gravitational field strength or the value of the gravity is given by force divided by mass or weight is equals to mg. So when we have objects, these objects experience the gravitational pull. The region around the object where other objects can experience the gravitational pull, that whole region is known as gravitational field. So force these objects experience in this gravitational field, we call that as weight. So what is the difference between the mass and the weight? Mass is amount of the matter, like how many particles are there, the number of the particle, amount of particle in an object, that's called mass of an object. But weight is a gravitational force, like we have an object, the force by which this object is being pulled toward the center of the planet, that is known as its weight. Mass of an object does not change until the object is broken or the particle composition change. Like when the evaporation occurs, the mass changes. Why? When evaporation occurs, the mass changes because the number of the particle change. In the beginning, in a hot liquid, you have more particle, but as the process of evaporation continue, the number of the particle decrease, so the mass will decrease. But weight of an object depends on the strength of the gravity changes from place to place. As we know, Earth is having a stronger gravity as compared to that of Moon. So the gravitational pull which the object experience on Earth will be different from gravitational pull the same object experience on Moon. So the weight of an object vary from place to place. The SI unit of the mass is kilogram, whereas weight is Newton. Mass is not having a direction, so it's a scalar quantity, where weight is a force, it's having a direction, so it's a vector quantity. And the formula which relate mass and weight, that is weight is equals to mass multiplied by gravity. And it is always acting downward from center of a mass of an object, or it is also acting toward the center of the planet. So this is the difference between the mass and the weight. Then experiment to determine the acceleration of a free fall. So how we can find the value of acceleration due to gravity or acceleration of a free fall? There are different methods which can be used, and one of them we can use an electromagnet. How we do this experiment? So first, the electromagnet is switched on. When the electromagnet is switched on, this steel ball will remain in contact with the electromagnet because steel is a magnetic material. So what is the initial velocity? Initial velocity is 0. Then what we did, we measured the height from the ball, the steel ball, till the tap switch. This is known as a tap switch. How it works, how this experiment will work. So the moment we switch off, this electricity of electromagnet, this steel ball will demagnetize. As the steel ball will demagnetize, it will start to fall. And the moment we switch off the electromagnet, the timer will start. And then what happened? The steel ball is falling, and once the steel ball hits this electromagnet is tap switch. So what will happen? This tap switch will change its position, and it will be like this. So when the tap switch will change, lose the contact the moment the steel ball hit, so that it loses the contact. Once it loses the contact, the timer will stop. So basically that is the time taken by ball to fall from this height h. So we have the time and we have the height. So we can use equation of motion. We have s is equals to ut plus half at square. S is the height, u is 0 because initial velocity is 0. So this whole factor will be 0. Then it will be 1 by 2. Acceleration will be equal to the gravity and t square. So if we know the height and we know the time, so we can find the gravity. But practically, this will have only one value. We'll have one value of height and one value of the time. So it will not be accurate. So we should repeat the experiment with different values of height and time. And if we repeat with the different values of height and time, then what can be done? We can compare with the equation of straight line y is equals to mx. So on y-axis, if I plot height, on y-axis, if I plot height, on x-axis, if I plot t square, then what will be my gradient? It will be a straight line because the gravity is constant and 2 is constant. So it will be a straight line from origin in which the gradient will be equal to g by 2. If gradient is g by 2, so gradient multiplied by 2, what we get? We get the value of gravity. So using this technique, we can find the acceleration due to gravity of a free fall object. Why we did not uh, use this formula directly? Because if we use the formula directly, we'll have one value of height and we'll have one value of a time. It will not be accurate. Is it clear? So this is the experiment to find the acceleration due to gravity by using the electromagnet, and to ensure the reasonable accuracy, the timer must be accurate to 0.01 second, the electronic timer which we use for accuracy. The height measured from the bottom of the ball bearing so that the size of the ball does not introduce an error. So when we measure the height, we should measure from this position. Why not the full ball? Because if full ball is there, then the size of the ball will also have value, and that will affect our final result. Then experiment should be repeated number of times to find an average, and the current on the electromagnet should be small. Why? Because if it's a large current, this will take longer time to demagnetize. If it take longer time to demagnetize, maybe you close the switch, or basically you switch off, but the steel ball will remain in contact because it is magnetized for a longer period of a time, so it will leads to an error. Is it clear, this idea? Finding the acceleration due to a gravity by using the electromagnet. Then we can also use a stopwatch and a ruler, a meter rule. So what we can do, we can place a meter rule exactly vertical on the floor. This is also another way of finding this acceleration due to gravity. So what we did, we'll drop an object from certain height, the measurable height, and instead of electronic timer, we can use stopwatch. So if we use a stopwatch, initial velocity is 0. The moment we release this ball, we will start the timer, and the moment it hits, we'll stop the timer. So we'll have the time, and we have this height we measured, and we'll repeat the experiment with different heights. Again, we have this equation of the motion, S is equals to ut plus half at square, in which the u is 0, so it will be S is equals to 1 by 2 gt square, or h is equals to 1 by 2 gt square. So on y-axis, if we have height, and on x-axis, if we have t square, our gradient will be equal to g by 2, or g multiplied by 2 will be gradient. But this method is not accurate. Why this method is not accurate? Because we are using the stopwatch, so our reaction time is also involved here. It's a very short time interval, so that our reaction time leads to an error. So how we can reduce our reaction time? So for that purpose, to reduce our reaction time, we can use a device known as light gates. So how these light gates work? So we can use light gates for improvement. The moment the ball crosses the first, because it will interrupt the light, the timer will start. And the moment it will cross the second one, the timer will stop. So using this idea, we can find the time interval to move from one light gate to another. But the difficulty, the problem with in using these light gates, that you need a whole system for that. So it's not like you can perform, you need, because the light gates are connected to a data logger, and that data logger is connected to computer. So you need the whole system for this if you want to use these light gauge. So advantage is that it is accurate, but disadvantage, it need a supply, it need the whole system set up to measure this time interval. So there is also another way which we can use, and we can use a camera or a digital camera, and we record this motion of an object when it is falling. So we place a camera here, and we drop an object from certain height. We measure the height, and so we measure the height. But how to get the time? Because the camera is having the picture rate, which is known as a frame per second. So using the frame per second, we can identify, or we can measure the time. Like example, if this camera is having say 5 frames per second, and when we take the video recording, it recorded say 15 frames. So what is the time interval? So 5 frame per second is, the frame per second is fixed for each camera. So if we know the frame per second for this camera, if 5 frames are there per second, so we can identify if 15 frames are there, how many second pass cross multiply, so it will be 3 seconds. So it will, the time interval to fall is 3 seconds. And what are other advantages of using the camera? We can zoom in to record the reading, and we can play back as well. Like we can record, we can just play back the recording, so we can have a more accurate result. And again we'll use the same formula, that h is equals to half gt square, in which we plot height on y-axis and t square on x-axis. So our gradient multiplied by 2 will be equal to g. Is it clear? All these methods to compare or find the acceleration due to gravity. So we can use electromagnet, we can use light gates, and we can use stopwatch as well as a video camera. Is it clear to everyone? So in exam they ask you to draw these or write the experiment and draw the experimental setup. So you have to practice this all. Then the Newton's third law. According to Newton's third law, forces always act in pair, or action and reaction forces are equal but opposite in direction. So whenever there are two forces, whenever force is there, it will always act in pair. Like example, you have an object which is lying on the floor. So if I say what are the Newton pair forces? So there is a downward force, the downward force by the object on the surface. And what will be the Newton pair force? Then as a pair force, there will be an upward force by the surface on the object. So there is an upward force by the surface. So one is force on object by the surface, and this one is a downward force on surface by object. So according to Newton's third law, forces always act on pair. And what are similarities between these pair forces? So what are the similarities between the pair forces? Number one, they are same type of forces. Like if one is gravitational, other one will be gravitational. If one is electromagnetic force, the other will also be electromagnetic force. If one is strong nuclear, other will also be strong nuclear. So forces always act in pair, and so these forces are same type. They are acting on a same line of action. You can see acting on the same line. They are acting on the same at the same time as well. And what is the difference between the pair forces? Their directions are opposite, and they're acting on different objects. As you can see, the downward force of the object is on the surface, so the upward force is there of the surface by the surface on the object. And another example, if we consider this is our earth and the object is placed on the surface of earth. So when we draw the Newton pair force, if we say weight, so weight is a gravitational force by the earth. So weight is a force on object by the earth. So if I say draw an arrow to show the Newton pair force of the weight, so then what will be the Newton pair force? The force of the object on the earth. So when you draw the pair force of the weight is a force by the earth on the object, and the pair force is, if you say F, so this F is equals to force on earth by the object. So forces always act in pair, and in terms of surface, when we draw, because it depends on what frame of reference we consider. So when we are considering the surface, so the downward force by the object on the surface, so same object, if we are considering the surface, so downward force is there by the object on the surface will be equal to upward force by the surface on the object. So if I say the value of the weight is 50 Newton, how much force object will apply on earth? That will be 50 Newton. And here in this example, because this object downward force is 50 Newton, which is a weight, so if the downward force is 50 Newton on the surface, the upward force will also be 50 Newton on the object. Is it clear? The concept of Newton pair forces? Then how we jump, how we explain, like how we are able to jump by using the Newton pair forces. So example, this is our earth and we are standing on the earth. I'm drawing a large size just to explain the idea. So we are standing on the earth. Earth is pulling us by a force. Example, our weight is say 600 Newton. So we will also pull the earth by a force of 600 Newton. And when we draw this in terms of surface, as we are standing on the earth still, because the downward force in this example is our weight, so downward force is the weight. So example, our downward force is 600 Newton on the surface. So surface is also applying 600 Newton on us. This is what surface is applying. So here the resultant force is 0. Here also resultant force is 0. So initially we are at rest. But how we are able to jump, how we can explain in terms of Newton pair forces. Less than a minute left, so I will share another link and continue this discussion. So we are discussing that forces always act in pairs, or Newton pair forces. So explaining the idea of a pair force, that how a person is able to jump in terms of Newton pair forces. So we'll consider a simple figure, like this is our earth and we are standing on earth. I'm not good in drawing, but it will be easy to understand. So what are the Newton pair forces in terms of weight? Because gravitational pull, So Earth is pulling this object by a force of 600 Newton, and this object will also pull the Earth by a force of 600 Newton. And when we compare the surface, because the frame of reference is very important, so when we compare the frame of reference compared to surface when a person is standing, so the downward force is actually his weight. So weight of the person is the downward force. So 600 Newton is a downward force, and 600 Newton will be the upward force by the surface on the object. So here resultant force is 0. Here also resultant force is 0. That's why the object will be at rest. But how we are able to jump? So if you try to jump, what is the first thing you do? You push the ground. Whenever anyone want to jump, you can feel this, that you have to push the ground. But what happens when you push the ground? So basically, when you push the ground, the downward force increased. As you try to push the ground, so as you try to push the ground, 600 is already downward. 600 is your weight, and you push, example, with a force of 100 Newton. So 600 is the weight and 100 is the force which you are applying on the ground. So what is the total downward force applied on the surface? So if the total downward force applied on the surface is 700 Newton by you, so how much force the ground will apply? The ground will apply a force of 700 Newton on you, because that's a Newton pair force. So if you apply total downward force is 700, which is weight plus your force, so the upward force will be 700 according to Newton pair forces. So when we see this figure, as you can see, our weight is 600 here. Our weight is 600 Newton, but because the ground is applying a force, the force from the ground, when you are pushing the ground, the force from the ground is 700 Newton. So force from the ground is 700 Newton, and the gravitational pull of the earth is 600 Newton. That's not the pair force, but that's a gravitational force which is acting downward. So what it create? It create a resultant force of 100 Newton upward. That is why you move up. Is it clear the idea how we are able to jump? So basically, the pair force of weight is not changing, but it create a resultant. When we push the ground is applying more upward force than our weight. That's why we are accelerating upward. Is it clear that how we are able to jump by using the Newton pair forces? So pair force of the weight is not changing, but pair force of the downward and upward force changes. And when we compare the upward force with the weight, because weight is a force of gravity which is pulling towards the center and the ground is pushing you upward, and that create a resultant of 100 Newton. That's why you accelerate upward. When we sketch a graph for the force applied, the normal contact force or the reaction force, and say time interval. So first we are standing still, like example, uh, say this is 100, 200, 300, 400, 500 and 600. So first when we are standing on the ground, say our weight. So first we are standing still. Earth is pulling us by a force. We call that as a weight. And the Newton pair force for the weight is the force which we apply on Earth. That is the Newton pair force. And when we compare the surface, so there is a downward force is there 600 Newton by the object on the Earth due to its weight, and that balances with the upward force of 600. That's, we are talking about the normal contact force, that is R. So in this case, the downward force and upward forces are same. So that's why it is a horizontal line. But when we start to jump, we try to push the ground. But when we are trying to push the ground, like we bend our knees, so in that moment our center of the gravity changes. So that's why short moment the weight, the downward force decrease. That's because when you try to bend your knees, the position of center of gravity changes. So the component of the downward force is there, not the full downward. But once you push the ground, why this dip is there? Because that's a slight change in gravity, center of gravity. But once you push the ground, it increases. So what is this value? Example, if this value is 700. So what does it mean? This 700. So first you was standing still on the ground, but now you try to push the ground. So when you try to push the ground, your force is 700, weight plus your force, that is 700. So upward force will be 700. So in this example, if the ground is applying a force of 700 Newton and our down weight is 600, so resultant force of 100 in Newton is there. And that causes the acceleration upward. So if we need the resultant force, so this is the total upward force and this is the total downward force. So if we need the resultant, and if they ask what is the weight, so this original value is the weight as well, and upward force minus downward force, what we'll get? We'll get our resultant force, which is equals to ma. Is it clear, this example? Then once you jump, you lose the contact, so you will not be in contact with the surface. That's why I did not complete the graph, but you can complete the graph and it will be this way. You will lose the contact, that's why the normal contact force will be 0. But this part is important. Why there is a dip? Because when you try to bend your to jump, you bend your knees. So position of the center of the gravity changes. The component of the weight which is acting a component downward. That's why you have a smaller value. But once you push the ground, higher downward force or more upward force, and that upward force is greater than the weight, which create a resultant force. So in the next session, we will do questions related to force, motion, and Newton laws. Any question related to the class today as we discuss the resultant force, the relation between mass and weight, and the Newton's third law. So I'll end the session and share this with you.